Swayam Prabha. Digital India. Educated India.
Good day everyone, welcome to the course on next generation sequencing technologies, data analysis and applications. In the last couple of classes we talked about differential gene expression analysis. We used DSEC2 to actually do the analysis, and at the end we actually looked at some of the results that we get from that analysis. So, when we looked at the results, hopefully you remember, right, we actually saw something called p adjusted. Okay. So, we saw the normal p value. Along with that, we saw something called p adjusted. Okay. And at that time I mentioned that p adjusted is something that we will discuss later. Okay. And this p adjusted is an adjustment based on something called multiple hypothesis testing. Okay. So, in today's class we will be talking about this multiple hypothesis testing correction, and we will talk about the methods that we can use to actually generate or to correct for this multiple hypothesis testing. Okay. And we will also generate the p adjusted. Okay. There are different methods, and at the end I will also mention which method we use for getting this p adjusted value in DSEC2. Okay. So, let us begin. So, here are the concepts that we will be talking about in this class. So, the first is multiple hypothesis testing correction, and the second is actually one of the methods that we can use for multiple hypothesis testing correction is called family wise error rate correction. Okay. So, these are the two topics that we will be covering in this class. So, just to remind you what we talked about in differential gene expression analysis. So, in the one of the integral parts of differential gene expression analysis is the hypothesis testing. Okay. We talked about for different methods how we can do this hypothesis testing, and especially for DSEC2 we use something called world test, right. So, this hypothesis testing for all genes in the samples cells and tissues, right. So, for all gene I, if you remember the notation, right. So, and this helps us identify genes for which the null model can be rejected. Okay. So, when you do the hypothesis testing, we have a null model and we also have an alternative hypothesis, right. So, the null hypothesis is that there is no difference in expression of gene I between the samples, right. So, these samples could be disease versus healthy, could be control versus treatment, etc. right. So, that is the null hypothesis, and based on this hypothesis testing we get this statistical significance, this p value, and based on that p value we can decide, okay, for which genes we can reject the null hypothesis, right. So, this actually helps us identify the genes that show difference in expression, right. So, again this is the most important part, right. We want to identify the genes that show difference in expression between, for example, diseased and healthy samples, right. So, these are the genes that we look for, right. This is the goal at the end. Now, this I is usually in thousands or tens of thousands, right, depending on the organism. So, if you are talking about simple bacteria like E. coli, we have 4,000 genes. If you are talking about yeast, it is 6,000. If you are talking about human, 20,000 to 25,000 genes. But if you talk about transcripts, right, so if you are also considering the isoforms, then that number would increase even further, right. So, this I is usually in thousands or tens of thousands. Okay. So, which means we are doing this hypothesis testing for tens of thousands of genes, right. So, this is a huge number of hypothesis testing. Okay. And we will see like what actually happens when you test so many hypotheses at once. Okay. Now, the question is then, of course, why do we need to do multiple hypothesis testing correction, right. As the name suggests, right, when you are testing a large number of hypotheses, you should do this correction. And by the way, this is not just applicable for differential gene expression analysis, this is applicable not just to biological science or medical science, this is applicable everywhere. Okay. In today's age where you are actually probably testing a lot of hypotheses, you need to do this multiple hypothesis testing correction, otherwise you will get erroneous results and you will get erroneous inferences. Okay. So, as you will see, right, you need to do this for all cases where you are testing multiple hypotheses and especially where you are testing a large number of hypotheses. Okay. So, the reason is very simple, is that testing a large number of hypotheses can lead to more false positive calls. Okay. So, I will mention what is false positive in a moment, those who are not familiar with all these concepts of statistics, and which means in our case we will identify many false positive genes, right, as differentially expressed. Okay. So, we will identify many genes and by the statistical test, and we will say okay, these genes are differentially expressed, but in truth, right, in actual scenario they are not. Okay. So, that means we are identifying them as differentially expressed when they are not, and maybe we will have some wrong inferences, right. We will, when we want to interpret the data further, we will make wrong inferences. Okay. So, we want to avoid these false positive genes or false positive calls, right, and this is true for many situations where you are doing this kind of multiple hypothesis testing. Okay, so, the question is now, how does testing a large number of hypotheses lead to higher number of false positives? Okay, I just mentioned that if you test a large number of hypotheses, you will get more false positive. So, the question is why, right, and how does this happen? So, I will show you two ways, right, this can happen. So, one is the number of false positives, right, total number of false positives that you can expect will rise if you test a large number of hypotheses. In addition, the probability for getting a single false positive will also increase manifold. Okay. So, these are the 2 points that I will just show you now. Okay. So, let us start with the idea of false positives, etc., right, if you are not familiar. So, in statistical test you have two types of errors. The first one is type 1 error and the other is type 2. Okay. And if you consider this table, right, so on one side on top you have actual situation, this is the actual truth. Okay. And you have H naught is true, the null hypothesis is true, and then you have the null hypothesis is false, right. So, if you think about differential gene expression analysis, some genes are differentially expressed in actual situation and some genes are not. Okay. So, you have H naught true, which means these are the genes that are not differentially expressed, and then you have H naught false where the genes are differentially expressed, right. So, our H naught, the null hypothesis was that the gene I is not differentially expressed, right, they are not showing any difference in expression between these two sets of samples. So, that is the actual situation, right, what is that what we call as the truth or ground truth. On this left side we have something called decision. Okay. Okay. So, what is this decision? So, this is the outcome from the statistical test, whatever test you are doing, right, whether it is world test or some other test, t test, whatever, right. So, whatever test you are doing, this is the decision, okay, based on the p value of the statistical test. Okay. And if the p value is below that certain threshold, let us say 0.05, we reject the null hypothesis, right, and then if the p value is greater than or equal to 0.05, we do not reject null hypothesis, right. So, that is the decision that we make based on the p value, right, from the statistical test. Now, imagine these situations, right. So, you can have 4 scenarios, we have the ground truth and the decision from the statistical test. Okay. Now, when H naught is true and we are not rejecting H naught, that is a correct decision, right, the statistical test is making the correct decision. When H naught is false and we are rejecting H naught, then that is also a correct decision, right. So, if a gene is actually differentially expressed and the statistical test is saying okay, this gene is differentially expressed, that is making the correct decision, right, these are correct calls. But then you have the two other situations, right, these two empty cells you can see here, right. So, the first one here, this H naught false, do not reject H naught, right. So, even though H naught is not true, the statistical test is not rejecting H naught, and similarly here when H naught is true, it is falsely rejecting H naught. Okay. So, these two are errors, right, the statistical test is making some error. Okay. And this, the first one is called type 1 error, and it's the number alpha is given, it is the probability of type 1 error, and then you have the second type of error where H naught is false and we are not rejecting H naught, that is called the type 2 error or beta. Okay. So, again beta is the probability of type 2 error. Okay. So, if this is clear, now which are the false positives and which are the false negatives, right. So, these are the false positives, right. So, H naught is true and we are rejecting H naught. Okay. So, what is the null hypothesis in our case is that the gene is not differentially expressed between two samples, but the statistical test is saying okay, this gene is differentially expressed. So, reject H naught. So, this gene is differentially expressed. So, this is a positive call, right. So, we are identifying this gene as a differentially expressed gene. So, this is a positive call. So, this is why it is false positive, right. So, this gives rise to false positives. On the other side you have the false negative, right. So, where you have H naught is false and do not reject H naught. So, we are not rejecting H naught. Okay. So, that is false negatives, and then of course, you have the true positives and the true negatives, which are the correct decisions. Okay. We are making correct decisions. So, that is why they are true positives and true negatives. Okay. So, once this is clear, now we will see, right, how this type 1 error can increase when you actually do multiple hypothesis testing. Okay. So, this is the situation for individual statistical test, right. So, you can imagine this scenario for each gene we are doing hypothesis testing, and you have this table, truth table, right. So, where you have the actual situation versus the statistical decision. Okay. So, let us now imagine this disease versus healthy gene expression pattern, right. So, what we do is statistical test between these diseased versus healthy samples. Okay. We determine this level of significance, and then we decide this threshold. This is actually decided by this alpha, okay, which is usually 0.05 or 0.01. Okay. This is related to the type 1 error. Okay. So, if p is less than alpha, then we can reject null hypothesis. If p is greater than or equal to alpha, then we do not have enough evidence to reject the null hypothesis. We have seen this. So, what it means is that when you set this alpha, we are expecting this, we are setting this probability of false positive call. Okay. So, we want to avoid or minimize this false positive call. Okay. So, imagine this single statistical test, and probability of type 1 error is alpha. Okay. And if alpha is 0.05, which is usually the case, then there is a 5% chance of type 1 error. Okay. So, that is how we are setting this 0.05. If you set this to 0.01, we have 1% chance of type 1 error. Now, imagine this situation, right, which we are doing in case of differential gene expression analysis. So, we have let us say 1000 statistical tests. Okay. We are doing this individual test for every gene that is there, and the probability of type 1 error is still the same alpha. We keep this threshold 0.05 for each test, and there is 5% chance of type 1 error in each test. Okay. So, this has not changed. So, alpha remains the same, but since we are doing 1000 statistical tests, given this 5% chance, we will expect about 50 type 1 error or false positives. Okay. So, you can see now, right, the threshold that we applied for single statistical test will not be able to contain this when you do this 1000 statistical tests, right. So, we will have a lot more error, false positive calls that is there, right. Now, the second situation is that it will also increase the probability of a single false positive call. So, we can look it in other way, right, again the same situation. Okay. Now, the probability of not making one type 1 error is 1 minus alpha, right. So, if probability of type 1 error is alpha, then probability of not making one type 1 error is 1 minus alpha. And let us say we are doing n statistical test, and the alpha remains the same for each test. So, since this test we are assuming they are independent, right, these statistical tests are independent. So, probability of not making one type 1 error we can multiply 1 minus alpha into 1 minus alpha, etc. right. So, this will be 1 minus alpha to the power n. Okay. Now, what does it mean, right. So, that is the probability of not making one type 1 error. So, if you want to calculate probability of making one type 1 error, this will be given by 1 minus alpha to the power n. So, we will get the probability of getting one false positive. Okay. So, earlier it was 0.05, right. Now, as n increases, the probability will approach the value of 1. Okay. As you can see, alpha is a fraction, right. So, alpha is 0.05, right, and 1 minus alpha is 0.95. So, if you make it 0.95 to the power n, then for n equals to 100, this probability becomes 0.994, right. So, what it means is that we are kind of sure now that if the probability is close to 1, right, that means we will definitely make one false positive call, right. So, that is the case here, right. So, as we do multiple tests, the probability of making this false positive call also increases manifold. Okay. Okay, so now we understand, right, okay, the type 1 probability of type 1 error would increase, right, when we are doing this analysis. Okay. So, how do you control this type 1 error, right? We do not want to make the increased type 1 error, right? We want to control this type 1 error, and there are two methods for this correction. One is family wise error rate correction, and the other is false discovery rate correction. Okay. So, you have FWER in short and FDR. Okay. So, what we will do now is we will actually talk about this FWER in this class, and then in the next class we will talk about the FDR correction. Okay. These are different approaches for controlling type 1 error. Okay. So, let us start with the family wise error rate correction, FWER correction. So, the idea is actually very simple here, right. Instead of setting the threshold to alpha for each statistical test, can we reduce the threshold for calling significance? Okay. Because we are doing 1000 statistical tests, and if we keep the alpha to be 0.05, we increase the number of false positives. But then can we reduce this alpha threshold, right? Instead of keeping it 0.05, can we make it lower, right, 0.01, 0.001 or even lower, right? And how do we actually do that? Okay. So, if you lower this threshold, right, that would mean we will again control the error rate, right. So, type 1 error rate. Okay. So, what happens is that the total probability of type 1 error remains the same after doing n test if you reduce this threshold. Okay. So, that is the idea, that we want to keep this threshold low, so that we do not make this type 1 error. Okay. And what we are doing is we are controlling overall type 1 error at alpha, which was 0.05 for single test. For 1000 tests, we also want to keep this overall type 1 error at 0.05. Okay. So, there are different methods for doing this. So, the first one is called Bonferroni correction, again named after the scientist who actually developed this method, and there is also foam Bonferroni correction. There are other methods as well, right. So, I will not discuss all those methods. What I will talk about are these two methods, Bonferroni and home Bonferroni corrections. Okay. So, these are the corrections that actually will keep the probability of type 1 error at alpha by changing this threshold for significance. Okay. So, let us talk about Bonferroni correction first. Okay. So, imagine this situation now, we have n hypothesis tests. Okay. So, then n could be 1000 or maybe 10,000, right, depending on the number of genes that you are testing. Okay. And for each statistical test, we have null hypothesis, okay, which we number as H01, H02, H03 and so on up to H0n. Okay. So, for you have seen this, for each gene we do the statistical test and we have a hypothesis, right, null hypothesis for each of those tests. Now, also imagine, right, we corresponding to all these statistical tests, we get these p values p1, p2 up to pn. Okay. So, once we have this, right, and also remember, right, probability of type 1 error in each test is alpha. Okay. So, the alpha is the probability of type 1 error in each statistical test. Now, the goal is to keep this alpha at the same level after doing these n tests. Okay. We do not want this alpha to increase or the number of false positives to increase. In Bonferroni method, the idea is very simple. Okay. So, let us change the threshold for significance lower, right, and how much lower? We set this to alpha over n. Okay. So, n is the number of statistical tests that we are doing. So, let us divide alpha by n. Okay. So, it is a very simple idea, and then what you do is that we check all these p values that we generated, right, and if pi is less than alpha by n, then we reject the null hypothesis H naught I. Okay. So, this is a very stringent requirement, right. We have lowered this cutoff now, instead of alpha we have made this alpha by n. Okay. And this will again depend on the number of tests that we are doing, right. So, if you are doing 100 tests, this would be alpha by 100, if you are doing 1000, this is alpha by 1000, right. And if we can reject this null hypothesis H naught I, then we can call this gene I to be differentially expressed, right, between diseased and healthy samples. For example, if you are doing this for disease versus healthy comparisons, right. So, again this is just an example, you can have the similar idea. What are the drawbacks of Bonferroni correction? Okay. So, one of the things you can probably imagine, right. So, if n equals to 10,000, right, for example, the threshold is 0.05 divided by 10,000, okay, and n is 10,000. So, it becomes 5 into 10 to the power minus 6. If you are doing more statistical tests, this value will be reduced much further, right. So, you will get maybe 10 to the minus 7 or 10 to the minus 8, those will be the cutoffs, right. And you can now imagine, right, if pi is less than 5 into 10 to the minus 6, only then we can reject null hypothesis, okay. So, this is a very stringent cutoff, and very rarely will get these pi values such low, right. And this is especially true for our scenario, right, where we are doing this differential expression analysis with very few replicates, okay. So, in the last class we talked about this number of replicates in the experiments, and we said it is about 3 to 5 replicates for each sample, okay. And if we have 3 replicates, it is very unlikely that you will get such p values, right, 5 into 10 to the minus 6, that kind of p value you will very rarely get, which means you will probably not detect differentially expressed genes, okay, with such low number of replicates with this Bonferroni correction, okay. And this is the problem that researchers faced, is that this is a very conservative method, right. So, it is very conservative, means for calling this or for rejecting null hypothesis, it sets a very stringent condition, okay. So, you need this p value to be very low, only then you get a significant call or a positive call, okay, where you reject the null hypothesis. On the other hand, what it means is that it commits a lot of high type 2 error, okay. So, it will get you will get a lot of type 2 error, means you will get a lot of false negatives, okay. So, if you remember this table, right, false negatives, where H naught is false, but you do not reject H naught, okay. So, in our situation, what it means is that the gene is differentially expressed in actual situation, that is the ground truth, but the statistical test here after Bonferroni correction is saying, okay, this is not differentially expressed, because the p value is very is not is lower than this, is not lower than this cutoff, right. So, which means we are calling a lot of false negatives, and we are not able to identify a lot of differentially expressed genes, actually differentially expressed in the real situation, okay. So, that means this sample has this method has low power, and we commit a lot of type 2 error, okay. So, what is the solution, okay. So, there is a solution that has been proposed, it is called Bonferroni method. So, this is a correction over the earlier method. So, the earlier method is very simple. So, you can apply it very easily, but then you see you will have a lot of problem, okay. So, this method also controls this family wise error rates at alpha, okay. So, you want this probability of type 1 error at alpha, okay. You do not want to commit false positive calls, right. And this method actually adopts a certain method that actually gives you less type 2 error compared to Bonferroni correction, okay. So, we will see in a moment, right, how we actually can generate or get more power, right, and commit less type 2 error compared to Bonferroni correction. So, what does it do actually? So, again coming back to the same situation, right, where we have this n hypothesis tests, okay. We have null hypothesis H naught 1, H naught 2, H naught 3, and so on, and you have p values, corresponding p values. For H naught 1 you get a p value of p 1 after the statistical test, for H naught 2 you get a p value of p 2 after the statistical test, and so on. And again the probability of type 1 error in each test is set at alpha, right. So, that was we are doing, right, and we want to keep this alpha for all these n tests, right. So, after comparing these n genes, right, for differential expression, we still want to keep the probability of type 1 error at alpha, okay. So, we do not want to have this increase, right, we do not want type 1 error to increase, okay. So, in Bonferroni method, the first step is to order the p values, okay. So, as you can see now, I am writing this p 1, p 2 within brackets, that means these are sorted p values, okay. So, p 1 is less than p 2, less than p 3, etc., right. So, and p n is the largest p value that we have from the statistical test, right. So, you are doing this 10,000 tests, you get p values, and then you sort the p values, okay, and you have the lowest p value first and the highest p value at the end, okay. So, you can create this sorted list, And similarly, based on this sorting, you also have the order null hypothesis, right, which we will call as H naught 1, right, within brackets, and then again you have H naught comma 2, H naught comma 3, and so on. Okay. So, what this method proposes is that instead of doing this alpha by n, right, where n is the number of statistical tests, compare these ordered p values with alpha by n, then alpha by n minus 1, and so on. Okay. So, what you do is then we start with, let us say, I equals to 1. Okay. So, for p 1, okay, this is the smallest p value, right, we compare with this alpha by n. Okay. So, alpha by n is the most stringent cutoff, okay, and p 1 is the lowest p value. Okay. So, for the lowest p value you apply the most stringent cutoff, okay, and then for p 2, this is the sorted value, right, you compare with alpha divided by n minus 1, okay, and then you continue this process. For p 3 you compare against alpha by n minus 2, and finally for the p n you compare with alpha by 1 or compare with alpha itself. Okay. So, in this case alpha is 0.05. Okay. So, what you are seeing here is that you are gradually shifting the cutoff, right. For each test the cutoff is different, okay, based on the original p value. Okay. So, again you sort these p values and you set these cutoffs, and these cutoffs are different for each test. Now, you apply these conditions, right. So, after you do these comparisons, you find the lowest k for which this p k, right, this is the ordered p value that is greater than equal to alpha divided by n minus k plus 1. Okay. So, let us say if p you find this as k equals to 10. Okay. So, alpha divided by n minus 9. Okay. So, you are comparing this and you see, okay, p 10 is greater than alpha divided by n minus 9. So, what do you do then? Okay. Once you find that, what you have to do is you reject the null hypothesis H naught 1 to H naught k minus 1, okay, and then you keep the hypothesis or do not reject the hypothesis H naught k to H naught n. Okay. So, you kind of now understand, right, because these p values are sorted, right, the first p value that actually crosses that threshold, right, or is equal to that threshold, then the rest of them after this p value, rest of the p values, they will automatically be greater than their cutoffs. Okay. So, that is why we actually keep this lowest k and find this lowest k for which this condition is satisfied, and then we reject the null hypothesis H naught 1 to H naught k minus 1, and we do not reject the null hypothesis H naught k to H naught n. Okay. So, again this method is less conservative. As you can see, we are changing the significance cutoff, right, say threshold for calling significance, and we are kind of changing that from most stringent to less stringent, right, based on the p value ordering. So, what are the drawbacks of this FWER methods, this family wise error rate, right. So, one is of course, this is very stringent control for type 1 error, right. We are even worried about committing single type 1 error, right, because we want to keep the overall alpha at 0.05, right. Even after doing these 10,000 tests, we want to keep this n at this alpha at 0.05. Okay. So, we are worried about even one false positive in out of this 10,000 tests, and as a consequence the type 2 error is higher in case of these methods, and we have reduced power. So, higher type 2 error means we have more false negatives, right, where H naught is actually false, but we are not rejecting H naught, right. So, this actually leads to a lot of false negatives. Okay. So, these are the references for this lecture. So, what we have seen is that multiple hypothesis testing increases number of false positive calls. Using two approaches we have discussed this, right, how that happens. So, we have also talked about now how we can do this correction, right, and so we have mentioned this hypothesis testing correction is required when we are doing this large number of hypothesis testings, right, and I have mentioned, right, this is not just applicable for differential gene expression analysis. You will see in other scenarios in the field you will have to do this multiple hypothesis testing correction, and beyond the field also wherever you are testing a large number of hypotheses you would have to do this correction. We have talked about the first type of methods here, right. We have mentioned there are two types of correction methods that exist. One is the family wise error rate correction and the other is false discovery rate correction. And in this class we have talked about family wise error rate correction, and we have talked about two methods that actually help us do this family wise error rate correction. The first is Bonferroni correction, right, and the second is Bonferroni method, and we have talked about the drawbacks. So, one of the drawbacks is that we actually do a very stringent control of type 1 error, but as a consequence we make a lot of type 2 error. Now, the goal is to actually try to balance these two and not to miss actually a lot of true positive genes. Thank you.